Hello and welcome to my channel and to the series ConQuiz 8 Concept Booster on Chemical Kinetics, and today we will be discussing part 5 of Chemical Kinetics, Understanding Kinetics through Multiple Choice Question part 2. All the questions are taken from previous year's papers of IIT-JAM and NET, as you know. In the last episode, ConQuiz 7, we have discussed MCQs on topics like units, orders, etc., on different types of plots, on half-life. And a few things were left. Today we'll cover in ConQuiz 8, Arrhenius equation, theory of kinetics, and mechanism of reaction kinetics. So let us start with Arrhenius. Let us have a quick review on Arrhenius equations. Gives you, temperature dependency of reaction as K, rate constant, A to the power minus E to the power T. A is the exponential frequency factor and E0 is the exponential factor, that is the active energy, and they are supposed to be independent of temperature, E0 and A. So the equation, if you take log, so it looks like this, and if you change the temperature from T1 to T2, assuming that K and E0 are temperature independent, then of course rate constants will vary and the equation looks like this. But suppose the temperature is constant and activation energies are different, maybe because of some presence of catalyst, etc. In that case too, the rate constants will change and the equation would look like this. We get all this from the first initial equation. And another third possibility is there, that where both E and frequency factor A, they are changing but at constant temperature, and that may happen that if you consider a reaction forward and backward, then E2 and E1 will be different, it will be different, and of course K1 and K2 would be different, and the ratio is equilibrium constant. So that would give you a measure of equilibrium. So on the basis of these three equations, we will quickly see some of the problems. The first one, rate constant for a reaction is given in the log form, and it's asked to find the activation energy of this reaction, right? So what you will do, simply start, these are the options. You will start from the equation as I have already shown, and then you take LOG, not LN. So 2.303 factor is coming, and you are comparing with the given equation log K, log K. So of course 114.1 is log A, but we are not interested in that, but this part is equal to E by 2.303 by R. So if you put 8.314 of R value, then you will get the activation energy in joules, and in kilojoules the answer you can check is going to be option A. Second question, for a reaction raising T. So this time temperature is changing from 200 to 300 Kelvin, and that results in increase of the rate constant with a factor of 2, and then it is needed to find the activation. So again another equation would be required here, that I have shown in the review. This is the equation. So all the values are given, T1, T2, 200, 300, etc., and K2 by K1 is 2. So you can find E, and R is given in as you know 8.314, etc. Fine. The next question, this time it is about the third option as I was talking about, that activation energy reduces by 12 kilocalorie in presence of enzyme. So assuming pseudo-first order kinetics, calculate the factor by which the reaction rate is increased, right? So of course this is going to be the equation, and if we can put E1 minus E2 is 12 kilocalorie, that means 12,000 calorie per mole, and all the other values are known. So the K2 by K1 you can easily check to be 5 into 10 to the power 8. So we can switch over to the next question. This time it's a forward and backward reaction I was talking about. difference between the activation energies of a reverse and forward steps is this much. If the pre-exponential factor of the forward reaction is double that of reverse reaction at the same time, the equilibrium constant for the reaction will be. So that equation, as I have already mentioned, that ln k1 by k2, which is actually the ratio k1 by k2, gives you the equilibrium constant. So a1 by a2 is given, e2 minus e1 is given. So everything is given on the right hand side. You can just put it to get the equilibrium constant to be the option B. So we can check it. Yes. So next question, the temperature dependence of a reaction is given by suppose this modified Arrhenius equation, A T square. So in that case, activation energy E0 is given by 1. So if you closely look, how do we get from this equation that this minus E by R, it is actually slope in a plot of ln k versus 1 by t. So ln k versus 1 by t gives you a slope minus E by R, and from that you can get E. Now the task is that suppose you have been given a k expression, different k expression. So again you have to have the slope, and that is dd. So slope of ln k versus 1 by t, that means you have to take the differentiation ln k with respect to 1 by t. So d ln k by d of 1 by t, and that is minus t square dt of ln. So now your task would be to start with the given k, which is this one. You take the log and then you evaluate the derivative dt of ln k, and then multiply by t square and put it in this equation and equate it with minus E by R. So that is the hint. So here it's solved also. So minus E by R you will get by evaluating all these steps and put finally n equal to 2, because I start with t to the power n, but it is t to the power square. So n equal to 2, and you will get E equal to E0 plus 2 RT, and that is option C. Option C. Okay. Next question. If the pre-exponential factor in Arrhenius equation is this, the value of the rate constant is at extremely high t will close to what? So this is rather a simple question, because if you just look at the expression, that exponential part t is in the denominator. So if t goes to infinity or very large, then this part would be 0. So e to the power this part would be 1. So that means k is equal to a. So k approaches a as t approaches large. So the given value is actually the answer, and that is option number A. That itself is the pre-exponential factor, and that also A. Well, next question, Arrhenius equations for two chemical reactions are this and that. So A1 and 2 are different, E1, E2 are different, but the condition given is E1 greater than, right? Then at a given temperature, which one is true? So we can start with this given equation, that K1 is this one and K2 is this one. So if you just take the ratio K1 by K2, so it would give you A1 by A2 and e to the power minus 1 by RT common, E1 minus A. Now we just mathematically see the conditions given. E1 is greater than, so the part bracketed by black color bracket, it is positive, and then minus 1 by RT. So the bracketed part by blue color is negative because the negative sign is there, and e to the power some negative, that means the yellow colored bracket, and that must be less than 1. So K1 by K2 is less than 1, that means K1 is less than K2, okay, the option is K1 by K2 is less than K1 by K2. So that is option A. Got it? Thank you. Now on theory of kinetics. So it starts with transition state theory, a single problem I'll discuss. According to the theory, the plot with slope equal to this is. So you have to start from the final equation of transition state theory, that you have to remember. K is this. So you see in the first part, this part, a t is there, but otherwise no t is there, and here in the exponentiation t is there. So if I want to clear t by dividing both sides by t, then I will get k by t. Now this first part becomes t independent and this part contains t. So of course I will have to take a log. So ln kt would give you, so log of this thing I am not interested in because t is not there, and this is minus delta h divided by r 1 by t. So a plot of ln k by t versus 1 by t would give you a straight line with a slope minus delta h by r as is given in the question. So our answer is ln kt versus 1 by t. So of course option C is that ln kt by versus 1 by t. So C is the answer. Okay. Unimolecular. Okay. So we are going to talk about Lindemann mechanism, unimolecular reaction, and K uni is the effective first order rate constant. This is the kind of mechanism proposed by Lindemann, and the slope and intercept of is given when the plot is 1 by k versus 1 by m. You have to find the value of the ratio k minus 1 by k2. Okay. So how we can solve this problem? Let us have a quick look of the mechanism itself, right? And the answer you will see that A 2 into 10 to the 5 would be the answer. Let us see how. So Lindemann proposed the mechanism finally through which we get the rate expression as k1, k2 and k minus 1 plus k2. So these rate constants are given in the mechanism, and this itself, the rate expression on the right hand side, can be written or rewritten as k prime a. So out of this a square, one a is left and the remaining part is called k prime, and so a is there, extra a coming out of the a square. So where k prime is obviously k1, k2 by this denominator into some one single a to the power 1, that means this one. So this is called the k uni or effective rate constant. Now this itself can be rearranged like this. So take the inverse. 1 by k prime is, so k minus 1 a by k1 k2 a. So a cancel out. So it gives you k inverse by k2 k1, and here k2 by k1 k2 a, that means k2 1 by k2 a. Sorry, this would be, I think, k1 a. Yeah, this would be k1. So plot of 1 by k prime versus 1 by a. So y axis is 1 by k prime and 1 by a is the x axis, and that would give you the slope 1 by k1, and intercept would be k minus 1 by k1. So if you look at carefully, then you will see that this intercept by slope would give you actually what is wanted in the question, k minus 1 by k, and the values are given of k minus 1 and k2, which are slope and intercepts and slopes respectively. So you can get the final answer to be 2 into 10 to the power 5. Okay. The next question, the first order rate constant for unimolecular gas phase reaction that follows Lindemann mechanism, so is given at two different pressures of reactant A. So what is the rate constant for the application step? So again the formula, exactly the formula that we have shown in the earlier slide. So here if you consider two reactions, that means k prime, suppose this is k2 and k1 for two reactions, and this part is constant, so they cancel out. So here you will get 1 by a2 minus 1 by a1, and all the values are actually given. So k1 prime and k2 prime are given 2 and 4 units, and a1 and a2 are also given 1 and 2 respectively. So we just put it to get and check the value that k1 comes to be 2 unit. That means option B is the correct answer. Similar question, the slope and intercepts 1 by r and 1 by s plot enzyme catalyzed reaction are 302 into the 5 respectively. No, this is not similar question. It's a different Michaelis-Menten mechanism or theory. It's talking about enzyme catalysis actually. So here again we will see the basic equations, and that is 1 by R is 1 by R max plus Km by R max into 1 by S. S is the substrate concentration, Km is the measurement constant, Y equal to Mx plus C. So from this we can see that the slope is Km by R max, but 1 by R max is C, so actually this is Km into C. So M slope equal to Km into intercept, that means Km is slope by intercept, so M by C. Now M and C are given 300 and 2 into 10 to the 5, so you get the constant 1.5 into 10 to the power 3. So option D is the correct answer. Okay. Now this is a similar question, V max or R max, whatever you say, and the constant Km are given. Rate of reaction when the substrate concentration is also given. So you have to find the rate of the reaction, right? So again we are going to use the same equation, Y equal to Mx plus C, and this time you see that R max is given, Km is given, and substrate concentration also given. So all the right hand side terms are given, so we can easily find 1 by R and hence R, and we can check that option B is going to be the right option. Okay, so please check it. Enzyme catalyzed reaction, another one. So here K2, this K2 is given, E0 is given, the magnitude of maximum velocity and turnover number using this Michaelis-Menten kinetics. So here it's straightforward application of the formula that R max is K2 into E0. So K2 is given and E0 is given. So it is simply, it would give you 3.42 into 10 to the power 2 unit, right? And turnover frequency, this is actually by definition this K2, this rate constant. So if you check, then of course option A is the right answer, right? So please check it. Now the last part of the session on mechanics, right? So for the following reaction, A reversible to B and B to C, dBdt is given by 1. So you see 4 options are there. Let us check. Answer is supposed to be B. Now dBdt. So from the first equation, half into dBdt is of course K1 into A plus, rather minus, because B is a constant here and it goes to A, so minus K inverse B square because 2 is there. So this is half dBdt. So dBdt is going to be 2 into K1A minus 2K inverse B square. But this is only for the first one. Again B is involved in the second equation. So here dBdt is given by minus K2 into B because B is a reactant. So minus sign is here. So overall dBdt you have to add this 1 and 2. So you get option B to be the right answer. Okay. So take your time, give pause whenever you need, and then please ponder on the question, the solution, and then come back to the video whenever ready. Well, it's a simple question. For the radical chain reaction below, the correct classification for step 2 and step 3 is respectively. So step 2 and step 3, if you see it carefully, then in both the steps, the radical H and the radical Br. So in both the steps, radicals are being formed. So that means propagating steps, both. So the C option is the right, because in both the steps, radical are being formed. Okay. Well, this is a typical example of this kind of mechanism which requires application of steady state approach, which actually applies for some short-lived intermediate of very low concentration, so much that the time derivative of that concentration of that intermediate is taken to be 0, and that is the actually mathematical form of the application of steady state approximation. And this intermediate may be experimentally verifiable, may not be. In some cases can find, So let us see how we really apply the steady state approximation. So here are the options for it, and the answer is supposed to be A. Let us see how it comes. So the reaction is 2NO plus O2 is 2NO2, and the proposed mechanism, as is shown already, that 2Na to N2O2, and this is an intermediate and not a reactant or product, and this N2O2 reacts with O2 to give finally N. So rate is actually ddt of NO2 half into ddt of NO2, because this 2 is there. So R is actually this. So if you are interested in ddt of NO2, then you have to multiply by 2, and that from equation ddt of NO2 into half is actually K2O2 N2O2, because this is the step where NO2 is involved. So K2 N2O2, okay, but you don't know the concentration of N2O2, which is an intermediate, right? So an interrogative sign is there. So how to get the concentration of N2O2? Here it applies the steady state approach. That means the time derivative of this intermediate concentration is 0, and time derivative of N2O2 how you will get? You have to check in which steps this N2O2 is there. So it is there in the first and forward and backward both the processes N2O2, and here in the second also. So you get this equation, and if you equate it with 0, then finally you will get N2O2 to be this. And the given condition, if suppose that you get a condition is applied now that K2O2, this one is much greater than K inverse. That means this second step is much faster than the deactivation of N2O2. Okay, so it may so happen depending on condition. In that case, this K inverse can be neglected. So it is finally K1 NO square by K2, and this is actually we were asking for. Now once you get this N2O2, then you can get R to be 2 into K2O2 and N2O2 from here. So finally you get ddt of NO2 is 2 into this. So finally you get the answer to K1 NO square. Okay, that is the option, one of the options given in the question. So now a few questions, very similar questions, only the application on what, SSA application on what, that is different. So for here, example here, in this case, you have to apply the steady state approximation on O, and you will get O to be K1 by K2, and finally R is in the second step, the slow step, O3 O into K2, and O is given by K1 by K2, so finally we will get K1 by O. So take it as an exercise. The next one is also a similar problem, so you can take it as an exercise. Here hints is given that you have to apply SSA on C this time. The next one is also an exercise because it's a similar problem, and here you have to apply the SSA on C, and you will get the answer, a right answer to be B. Please do it, give pause and do it, come back when you are ready to answer. Well, for a sequence of consecutive reactions, this is another type of reactions, A to some intermediate I to P, okay, K1 and K2. So how I will change? By steady state approximation again. So steady state to be applied on I naturally, so dIdt is 0. Now I is involved in both the process K1 and K2, so K1A minus K2I, so equating it to 0, you will get I to be K1 by K2. So option D is the answer, K1 by K2. Okay, rather simply. Photochemical decomposition of hydrogen iodide takes place with the mechanism. So this is the photochemical step, first one. So the rate involved depends on the IA, intensity of absorbed light, and the second step is thermal. So H plus H is H plus I. now considering both H and I as intermediates, the rate of removal of HI. So rate of removal of HI, that is minus ddt of HI. So HI is involved in both the steps, in this first and second step. So accordingly you can get that R is in the first step, it is minus ddt of HI is of course IA, simply IA, and the thermal process it is K1 into H into HI, K1 H, right? And now if we apply SSA on H, so you will get that IA is IA minus KH into HI on H if you apply. So and make it equal to 0 to get IA equal to this K1 H HI. So in equation 1, HI K1 is actually IA. So finally it becomes R equal to IA plus I. That means 2IA. So option C is the right answer. So hope you have enjoyed the MCQ sessions, the last and present one. Thanks for watching. Our next video would be on different topic. Again, it's going to be a series of maybe 4 or 5 episodes, and that is on much awaited omnipresent subject thermodynamics. We'll start in session 9 part 1 as usual with rapid fire conceptual question and answer, true false kind of questions and answers. So please keep on watching, do subscribe, encourage your friends to subscribe, to watch and to learn and apply in exams. Thank you very much. See you soon.